In this video, we're going to start a series on thermochemistry. Thermochemistry, if you take the word apart, chemistry, obviously that's changes in matter, but thermo is a word that's related to heat, which is the word that was often used and sometimes still is used to really mean energy. So we're looking at how energy and changes in matter are related. So today we're going to start out with some basics, mostly some definitions, some terminology, things like that. And then we're going to talk about a concept called calorimetry. Meter means measure, and calor means heat, or is another way of expressing the idea for heat or energy, so it's energy measurement. Calorimetry is the primary way that chemists use to determine how energy and matter changes are related to each other. So first of all, let's define what energy is. It's not so easy to give a very simple definition of energy. Energy is a kind of an abstract concept, but we can describe it in a few ways. One thing that's true of energy is that it's quantifiable. You can actually measure it. We have many ways of measuring this. Energy can be measured in joules or BTUs or calories. There's lots of different quantities that can be used to measure how much energy is present in a system. It also is conserved. So we're going to make use of the law of conservation of energy, otherwise known as the first law of thermodynamics, and we're going to assume that all the energy in the universe is constant. So if there's change in the energy of a system, that can only be because energy moved into that system from somewhere else in the universe or moved out of the system into the universe. It's storable. In a bit, we're going to talk about the ways in which energy can be stored. And it's transferable. So you can move it from one system to another system, or you can move it from the system to the surroundings, or you can move it from place to place within a system. And this is basically the closest we can get to a definition of energy, is that it is a potential to cause change in three measurable quantities. One is temperature. If the temperature goes up or down, there's probably been an energy interaction going on. Velocity, if something speeds up or slows down, starts moving, stops moving. Those are all indications that there's been some energy involved. Or the position in a field, like a magnetic field or a gravitational field, for example. Let's talk about 4 common energy storage modes. One energy storage mode is energy that's stored in the motion of the particles. This is called kinetic energy. The abbreviation that I use for this is EK, and it's related to the mass and to the velocity of the particle. So specifically, kinetic energy is the mass of a particle times the velocity of that particle squared divided by 2. Now this is talking about the type of energy storage where all the particles are moving in the same direction. And this is macroscopic, so throwing a baseball or a car moving down the road or something like that. Thermal energy is microscopic. So this is the energy of the motion of particles, but when they're moving in all random directions. So thermal energy storage could be high even if the object itself is standing still, because all these particles are moving around in random directions that sort of cancel each other out, but they still have motion. And the energy that's stored in that random motion is what we call thermal energy storage. This is going to be proportional to how much matter is there, the mass, and to how hot it is, the temperature. The faster the particles are moving, the higher we say the temperature is. And then there's positional energy storage, storage in the positions of particles. This could be elastic energy. Elastic energy is stored when an object that is deformable in an elastic way, in other words, it will go back to its original position, gets stretched, or gets compressed. And the amount of energy storage is going to be proportional to how much that stretching or compressing occurred. Not a big deal in chemistry. We're not going to see that very often. And then there's also positional energy storage in the positions of particles in fields. One of these is a gravitational field. Another one is magnetic. And a third one is electrostatic. And this is the one that's the most important for our purposes. But all of these share in common with each other a sort of a math pattern that they all follow. The energy storage is proportional to the product of 2 properties multiplied together and then divided by the distance between the 2 objects that are storing this energy in their positions. We have already seen the most important one of this for us, which is Coulomb's law. That's the electrostatic energy storage model, where we know that the energy is going to be proportional to the charge on one object times the charge on the second object divided by the distance between them. So that isn't Coulomb's law, but that's derived from Coulomb's law and the definition of work. Electrostatic energy storage is the most important of these field positional energy storages to chemistry, and there are two significant microscopic versions of this in chemical systems. One is what we call phase energy, and this is when the particles are attracted by intermolecular forces. So this could be dispersion forces, dipole-dipole interactions, could also be hydrogen bonding, which is much stronger. And this is the energy that has to be overcome when you make a phase change occur, like melting or vaporizing. And then there's chemical energy storage. And this is when the particles are attracted by chemical bonds, like ionic bonds, covalent bonds, or metallic bonding. The total amount of energy stored in a system or an object is often unknowable because we have so many factors to keep track of. One of them is the speed that an object, even if it's sitting still, has because of the fact that it's on the surface of a planet with a big radius that's spinning around its center once per day. And then that planet is also going around the sun at a very large radius once per year. And the whole solar system is probably moving through space at very difficult to measure speed. So we can't really know the total amount of energy storage. So we're going to most often be interested in the changes in the energy storage. And how we're going to do that is by measuring the energy transfer from system to surrounding. So if you know how much energy went out of or into a system, you can know how much its total energy storage changed. And that's usually what we're focusing on. Okay, so let's talk about energy transfer. There's one way that energy can be transferred that we call working. And this is when mass is moved against a force. In a linear system, this could be thought of as the force required to move an object through a distance, delta x. So delta x is the change in position, and the product of that force that's required and the distance that it's moved through is what we call work. That's what the quantity is, but the energy transfer mechanism is what I would call working. In a three-dimensional system, like when a gas expands, and this is very common in chemistry, work is expressed a different way. It's the product of pressure times change in volume. Another evidence that energy has been transferred is when the temperature changes. That energy transfer might be through heating, which we abbreviate as a Q. And for this to be the energy transfer mechanism, there has to be contact between the hot and cold objects or systems. Now that contact may be indirect. So in this example that we see here, the coffee is warming up the air by direct contact, but it's also warming up the coffee cup, which is warming up the air indirectly. So the contact doesn't have to be a direct contact. Lots of people will use the word heat, and what they really mean is the quantity of energy transferred through heating, through the heating mechanism. When temperature changes, it could also be that the energy transfers through what we call radiation. And the difference between radiation and heat as quantities of energy transferred is that there isn't necessarily any contact required for radiation to be the energy transfer mechanism. So, for example, the sun is in no way in contact with someone laying on the beach, but they still warm up because of the energy transferred from the sun. So that is radiation, that's electromagnetic radiation that's being moved through space, and you don't have to have any contact for that to occur. Heating is far more common in general chemistry, and for all practical purposes, we can treat radiation and heating as if they are the same kind of energy transfer. Measuring energy. Let's look at units. There are some units that are based on working. Force is typically measured in the SI system in newtons, and displacement or change in position would be measured in meters. And so if you think about those two quantities put together, 1 newton of force pushing an object through a meter, that's an energy unit. And a newton meter has been renamed the joule after a scientist who did important work in energy studies. But then if we think about energy transfer through working in the chemistry situation, where it's pressure times volume, a unit that would make sense is liters of volume change and atmospheres of pressure. So to try and translate this back to the physics units of work, which were joules, you might remember when we were studying atmospheric pressure that 101,325 pascals is 1 atmosphere. But a pascal is a Newton per square meter. Now let's think about liters. What's a liter? So a liter is 1,000 cubic centimeters. Let's convert that into cubic meters. So a cubic meter is 100 centimeters by 100 centimeters by 100 centimeters. So that would be 100 cubic centimeters would be the equivalent of 1 cubic meter. And that comes out to 0.001 cubic meters. So if an atmosphere is 101,325 newtons per square meter, and a liter is 0.001 cubic meters, then we can multiply these together, and meters squared will cancel out, and we will get Newton meters, which is what joules is. And the number is 101.325. So there's 101.325 joules. That's the equivalent of 1 liter atmosphere. So that's a conversion factor. We can get another conversion factor from the 2 units that we've been using for R. R, remember, is 0.0821 liter atmospheres per mole Kelvin. That's R. But it is also 8.314 joules per mole Kelvin. And moles and kelvins are the same in both sides, so we could say that 0.0821 liter atmospheres is the same as 8.314 joules. These are actually exactly the same ratios. So those are units based on working. Now let's look at units that are based on heating. Imagine that we're heating up a substance by adding some energy to it, and after some time, the substance goes up by some temperature. The more we let that sit over that burner, the more energy we add to it, the higher that temperature is going to go. So it's pretty reasonable to think that the amount of energy that's added through heating is going to be proportional to the temperature change. But also, if we had 2 different quantities and we raised them by the same temperature, the one that has the more mass is going to require more energy to get up to that same temperature. So it's very reasonable also to think that energy transfer through heating is proportional to mass. So if we put those 2 together, energy transfer is proportional to mass and temperature change. Now let's look at 2 different substances. Let's say we have this blue substance that we have the same mass as the green substance in the right-hand beaker, and both of them are raised to the same temperature change, but it takes less time at the same rate of adding heat for the green substance to heat up to that same temperature as it does for the blue substance. If we were to make a graph of that, this is what it would look like. To get up to whatever that final temperature is, takes less energy transfer for the green than it does for the blue. The slope of this line, if we have a fixed mass and a fixed temperature that we're getting up to, is a way of measuring how good each substance is at resisting temperature change. That's called the specific heat capacity. So this blue substance has a greater resistance to temperature change. It takes more energy to raise that substance to the same temperature than the green substance. So the green substance has a lower specific heat capacity. So that's the constant of proportionality that turns this general proportionality into an equation. The specific heat of water is defined in order to create an energy unit, and that energy unit is called the calorie. If you can take 1 gram of water and raise it by 1 degree C, it takes 1 calorie of energy to do that. So that's the specific heat of water. It's 1 calorie per gram per degree C. An experiment was done, and here's kind of a schematic for it. You drop a weight, which is being pulled on by gravity, so that's a force that we know, and you measure how far it falls, so that's a delta x, and that allows you to get a F times delta x. And so this would give you the physics unit of energy, which would be joules. But that's attached to this paddle wheel that spins around as the weight falls. And there's a temperature inside of this liquid, in this insulated container, that the paddle wheel is increasing the temperature of by literally moving the particles around physically, by mechanically making them move faster. And that will cause the temperature to rise up. And if you measure very, very carefully, then you can make a relationship between joules and calories, because the temperature change will allow you to measure how many calories of energy were added to this system, and the amount of energy that was lost in joules could be measured by force times delta X. So this is a way of modeling this with the LOL chart that you learned about in freshman science. If you have a lower amount of thermal energy before this experiment, and then later on you have a higher amount of thermal energy, it is because energy was added through working. So we can find the change in thermal energy by the specific heat equation. That's specific heat times mass times temperature change. We can measure this, we can measure this. We know this is water. And we can find this by the physics equation, F times delta X, and then we can make a conversion. So what they found out was that 1 calorie is the equivalent of 4.184 joules. So the specific heat capacity of water then is 4.184 joules per gram per degree C, because a calorie and 4.184 joules are the same amount of energy. In an earlier video, we talked about the difference between intensive and extensive properties. Specific heat capacity is an example of an intensive property. The specific heat capacity of a substance, no matter how much of it you have, is always going to be the same because it's per unit of mass. Heat capacity is an extensive property. It depends on how big the mass is. So heat capacity would be specific heat capacity times mass. You're taking the mass out of the denominator here. Or another way you can think about it is it's the ratio of how much energy is transferred to how much the temperature goes up. Heat capacity is useful because sometimes you have an object that's made of more than one substance. And so then you can account for, some metal, some liquid, some gas, whatever is all involved in this system. You can just ignore all the individual specific heat capacities and just look at what is that object's ability to resist temperature change as the heat capacity. And then if you wanted to evaluate how much energy was transferred into or out of that object, it's just the heat capacity times the delta T. So it's very equivalent to this, except heat capacity is extensive, doesn't depend on mass, and specific heat capacity does depend on mass. Okay, so what we use this for is this process called calorimetry, which literally means energy measurement or heat measurement, more precisely. So it's used to measure energy transfer through heating. Here's the basic idea. You divide the entire universe into two parts. One is the system, and the other part is the surroundings. The system is going to be very small, usually. It's the thing that we're interested in knowing about, and the surroundings is very big and complicated. And the idea is that as energy transfers in or out of the system, then we can measure that energy flow by tracking the temperature change of the surroundings. Now, there are some serious practical measurement technicalities involved in measuring what's happening to the whole entire universe outside of your little system. So how we solve that problem is by restricting the surroundings to a smaller area by insulating them. So this is not permanent, but if you work fast in the short term and you use good insulation, you can restrict the entire universe that you're trying to study into this much smaller fake universe. So this is a practical way that this could be set up. You have your system, which could be as simple as a piece of matter, like a block of metal or something like that, or it could be as complicated as a reaction that's occurring. And then you have your insulated container that restricts the universe to everything inside of this container. A styrofoam cup works pretty good if you're not being super precise and if you're careful about it and you work fast. And then also inside that container is the surroundings, which is some substance that has a known specific heat capacity and unknown mass. Lots of times this is water. There are some kinds of oils that are used as well. And if you're going to be really careful, you have to think about the heat capacity of the stirring bar that's in there. In this case, there's a stirring bar that is going to keep everything equalized, and the thermometer itself and the insulated container. So that can all be accounted for as well. And then if you think about energy transfer, if you have, for example, a system that gives off energy, then that means your system is going to lose energy storage, and that energy is going to go out of the system and into the surroundings, and then that means that the surroundings are going to gain the equivalent amount of energy. Why is it the same amount out of the system and into the surroundings? Because we insulated this container, and there's no other way energy could get into or out of the surroundings except if it came from the system. So that means that the system energy loss is equal to the opposite of the surroundings energy gain. And then we can use that to measure how much energy storage change occurred in our system. So let's do an example problem. Let's say we have a piece of metal that has a mass of 27.5 grams, and we have this piece of metal in an oven, and we heat it up until its temperature is 99.57 degrees. Then we quickly take that piece of metal out and we pop it into an insulated container that contains 265.47 grams of water, and it's originally at 24.69 degrees. The temperature is going to go up because we put a hot piece of metal in there, and when it reaches its final highest temperature, it's at 26.34 degrees. We want to know what the specific heat capacity of the metal is. So the specific heat capacity is going to be equal to Q divided by mass times temperature change. We can know how much the temperature of the metal changed because we knew that it was originally at 99.57, and in the end it got to 26.34. We know the mass is 27.50 grams. What we don't know is how much energy flowed out of the metal. But we do know that the amount of energy that flowed into the water, which is the surroundings, is going to be the same quantity of energy that flowed out of the metal. So we will figure that out. Q for water, which is going to be equal in size, but opposite in sign, to the Q that flowed out of the metal, would be equal to the specific heat of water, which is 4.184 joules per gram per degree C, times the mass of water, which was 265.47 grams, times the temperature change of the water. And it went from 26.34, or to 26.34, from 24.69 degrees C. So when we quantify all that, the Q that went into the water ends up being 1,833 joules. Okay, so now we know everything we need to find the specific heat capacity of the metal. Energy transfer through heating was 1,833 joules. The mass of the substance was 27.50 grams. And the temperature change was 99.57 down to 26.34 degrees C. And we calculate this all out, we get 0.09102 joules per gram per degree C. So that's a practical application of calorimetry. Now let's start to take into account working as well as heating, because a calorimeter only measures energy transfer through heating. The total amount of energy transferred out of or into a system is equal to the sum of the energy transferred through heating and the energy transferred through working. If you have a situation where working is possible, in other words, the volume can change, this would be a constant pressure situation, volume can change, then the amount of energy that you're measuring in your calorimeter is not equal to the total energy exchange, because calorimeters can only measure Q. So Q that's measured in this situation is labeled QP, or Q at constant pressure, and this is the kind of calorimetry called constant pressure calorimetry that we were doing in the last example. We weren't accounting for work because working will probably not be significant if it's just a piece of metal inside of a cup of water. However, there are some situations where working is not possible. This would be a constant volume situation. If you can't expand or contract the system, then that means there is no working. And so you are measuring, if you measure the energy flow through heating, you are measuring all the energy exchange. So Q in this case would be labeled QV, or Q at constant volume, and this kind of calorimetry is called bomb calorimetry. So this is a bomb calorimeter. It's basically just like a regular calorimeter, except for immersed in the water, you have this vessel that's made out of something hard and rigid so that the volume cannot change. You still have a stirrer in there to keep things equalized. You got a thermometer in there to measure temperature change. You're still going to have water or oil or something of known specific heat capacity and mass. But then you cause this reaction to occur inside of this container that can't expand. That's the bomb inside there. And therefore, when you measure the temperature change of the surroundings and then calculate the energy flow through heating, you are measuring all the energy exchange. This is a picture of actual bomb calorimeter parts. That's the bomb. So there's a little sparker in here. So that little gap can have a spark go across it, and that can ignite a reaction. And then it's all sealed up with gaskets and stuff so that you put some substance in there, basically explode it. The bomb doesn't break because it's made to be rigid enough, but all the energy that flows out of it is measured by the calorimeter. So here's an example problem. Crackers dried and ground, put in a bomb calorimeter with pure oxygen. The heat capacity of the bomb is given. It's 923 joules per degree C. And it's in 800 grams of water inside of that calorimeter at 25 degrees C. The temperature of the water rises up to 38 degrees C after the cracker is combusted. And we want to know what's the energy content of a serving of 9 crackers in kilocalories. So the change in energy, the energy that came out of this system, which is the crackers, is equal to the energy that went into the water and the energy that went into the calorimeter. So that's the heat capacity of the water, which is 4.184 joules per gram per degree C, times the mass of the water, which was 800 grams, times the temperature change of the water. It went up by 13 degrees C, because it went up from 25 to 38.1, 13.1 degrees C. And then the calorimeter had a heat capacity of 923 joules per degree C, and it also went up by 13.1 degrees C because everything's going to be in thermal equilibrium at the end. So that comes out to 55,900 joules that came out of the crackers. So that's the energy content of the crackers. Well, it's one cracker. So we want to, first of all, take 35,900 joules, and we want to multiply by 9, because this was joules per cracker. So we're multiplying by 9 crackers. And then we want it in kilocalories. So let's convert from joules to calories. There's 4.184 joules in 1 calorie. And we want kilocalories. So there's 1,000 of anything in a kilo thing. So that's 1,000 calories per 1 kilocalorie. And now our units are all going to come out, and it's going to be in kilocalories. And that ends up being 120 kilocalories.